Welcome to Math on Ice, June 2012 Integral Equations. We will see one question from part B and one question from part C. For the linear integral equation phi of x is equal to x plus integral 0 to 1 by 2 phi of zeta d zeta. Now we will write in the convenient form y of x is equal to x plus integral 0 to 1 by 2 y of t dt. I've replaced phi by y and zeta by t. They've asked us to find the resolvent kernel r of x comma t comma 1. So the formula for the resolvent kernel is r of x comma t comma lambda is equal to summation n is equal to 0 to infinity lambda power n k n plus 1 of x comma t, where k n plus 1 of x comma t will be equal to integral a to b k of x comma t into k n of x comma z into k n of z comma t into dz. Now here our kernel k of x comma t is equal to 1, and that implies k1 of x comma t. We need to find k2 of x comma t, which is equal to integral 0 to 1 by 2 k of x comma z into k1 of z comma t into dt, which is equal to integral 0 to 1 by 2 k of x comma z will be equal to 1 and k1 of z comma t will be equal to 1. So we get 1 into 1 dt. It will be t 0 1 by 2. We get 1 by 2. And k3 of x comma t will be equal to integral 0 to 1 by 2 k of x comma z into k2 of z comma t into dt, which is equal to integral 0 to 1 by 2 1 into 1 by 2 into dt, which will be equal to 1 by 2 t 0 1 by 2, which is equal to 1 by 2 the whole square. Similarly, when you find k4 of x comma t, you will get it as 1 by 2 the whole cube. And similarly proceeding, you will find kn of x comma t is equal to 1 by 2 the whole power n minus 1, and kn plus 1 of x comma t will be equal to 1 by 2 the whole power n. Now, as we know, the resolvent kernel x comma t comma 1 is equal to summation n is equal to 0 to infinity lambda power n k n plus 1 of x comma t. Here lambda is equal to 1 given, so we get 1 to the power n. So summation n is equal to 0 to infinity 1 by 2 the whole power n. This is a geometric series. This is actually equal to 1 plus 1 by 2 plus 1 by 2 the whole square plus 1 by 2 the whole cube and so on. Since 1 by 2 is a number which is strictly less than 1, we get the summation of the infinite series as 1 divided by 1 minus 1 by 2, which is equal to 1 divided by 1 by 2, which is equal to 2. So the answer is 2. The next question is the integral equation phi of x is equal to lambda times of integral 0 to pi kernel of x comma zeta phi of zeta d zeta. They have defined the kernel separately for the interval 0 to t zeta separately and zeta to pi separately. Now we will write in our convenient form phi of x is equal to lambda times of integral 0 to pi k of x comma t into phi of t dt. Kernel x comma t is defined to be, which is equal to cos x sin t 0 less than or equal to x less than t, and then cos t sin x for t less than or equal to x less than or equal to pi. Now we need to replace k of x comma t in this. First we have to separate the integral limit 0 to pi. We need to put the limit for t. So it must be in the variable of x, 0 to x and then x to pi. But we have the limit in terms of 0 to t and t to pi. We may not apply the same limit here because here we have t in the integral. So we need to make the integral limit with respect to t, right? So we need to have the integral from 0 to x and x to pi. But we have to replace this t by x and x by t first. So replacing t by x and x by t in this kernel, we get k of x comma t is equal to cos t sin x 0 less than or equal to t less than x, and cos x sin t x less than or equal to t less than or equal to pi. Now we are able to replace the k of x comma t here in the integral equation. After this, they have given the boundary value problem phi double dash of x minus f of lambda into phi of x is equal to 0 with the boundary condition phi of pi is equal to 0 and phi dash of 0 is equal to 0. We need to find the f of lambda, which is a known function, and we need to verify the boundary value problem has a unique solution or infinitely many solution or no solution. First we will find kernel in this equation, integral equation, and then we will evaluate phi of x, and then we will take the Leibniz rule to evaluate phi dash of x and phi double dash of x. Finally we will find the value of f of lambda, and then we will determine whether it is having unique solution or infinitely many solution depending on f of lambda. Here phi of x is equal to lambda times of integral 0 to x. So t varying from 0 to x, we have to consider this one, sin x into cos t. So we will have sin x cos t into phi of t dt, and then plus lambda times of integral x to pi x2 pi cos x into sin t. So cos x sin t phi of t dt. This is equal to phi of x is equal to, take out lambda completely, integral 0 to x sin x cos t phi of t dt plus integral x2 pi cos x sin t phi of t dt. Apply Leibniz rule to take the differentiation. Phi dash of x is equal to lambda times of integral 0 to x dou by dou x of sin x cos t phi of t dt plus the upper integral plus the differentiation of the upper integral is equal to 1. D by dx of upper integral is equal to 1, and then the remaining this f of x will be sin x into cos x into phi of x. Lower integral, differentiation of the lower integral will become 0, minus the differentiation of the lower integral will become 0. Next, for this one, plus integral x2 pi dou by dou x of cos x sin t phi of t dt plus the upper integral. The upper integral, the upper limit is pi. So the differentiation of a constant will be 0 minus the differentiation of the lower limit, which is equal to d by dx of x into cos x sin x phi of x, and this is equal to lambda outside integral 0 to x. Differentiation of this term will give you sin x differentiation is cos x. So integral 0 to x cos t phi of t dt plus sin x cos x phi of x, and then plus integral x2 pi. Differentiation of this term is going to give you minus cos x, minus sin x. Differentiation of cos x is minus sin x. So minus sin x sin t phi of t dt minus cos x sin x phi of x. Here these two terms are same and opposite in sign, so they both cancel each other. We get phi dash of x is equal to lambda outside integral 0 to x cos t phi of t dt plus integral x2 pi minus sin x sin t phi of t dt. Now taking again a differentiation to get phi double dash of x, which will give you lambda outside integral 0 to x. Differentiating here, we get minus sin x cos t phi of t dt, and applying the upper limit, we get plus cos x phi of x, and here taking the integral, taking the differentiation of this part, we have plus integral x2 pi minus cos x sin t phi of t dt plus, we get minus into minus will be plus sin x into phi of x. And finally, phi double dash of x is equal to lambda times of minus lambda times of integral 0 to x sin x cos t phi of t dt plus integral x2 pi cos x sin t into phi of t dt, and then plus lambda times of cos squared x plus sin squared x into phi of x. So phi double dash of x is equal to minus lambda times of, this is integral 0 to x sin x cos t phi of t dt, x2 pi cos x sin t phi of t dt, which is exactly your phi of x. Integral 0 to x, this part, this will be your phi of x. So phi of x is equal to lambda times of the whole thing, right? So this will be minus lambda times of this will be minus phi of x. And this would be plus lambda times of phi of x, because cos squared x plus sin squared x is equal to 1. So phi double dash of x is equal to, phi of x can be taken outside, 1 minus 1 plus lambda. We get lambda minus 1. Phi double dash of x is equal to phi of x into lambda minus 1. When you take this part to the left side, we get phi double dash of x minus of lambda minus 1 into phi of x is equal to 0. We get the function f of lambda is equal to lambda minus 1, because in the boundary value problem, it is given phi double dash of x minus f of lambda into phi of x is equal to 0. So we get the f of lambda to be, f of lambda is equal to lambda minus 1. Now they have also given some boundary conditions, and also they have asked us to verify whether they have an unique solution when lambda, f of lambda is equal to 0. If f of lambda is equal to 0, what happens? This is our equation. From the option A, f of lambda is equal to 0. We get phi double dash of x is equal to 0. Write the auxiliary equation. We get m squared is equal to 0. That implies m is equal to 0, 0. So we get the answer phi of x is equal to a into e to the power 0x plus bx e to the power 0x, which is equal to a plus bx. And applying the boundary conditions, phi of phi is equal to 0, phi dash of 0 is equal to 0. So phi of pi is equal to 0, phi dash of 0 is equal to 0. Just determine phi dash of x, which is equal to a differentiation will go off, it is a constant, so bx will give you b. Phi dash of 0 is equal to 0, phi dash of 0 is equal to b, which is equal to 0, so we get b part to be 0. Phi of pi is equal to 0, so we get phi of pi is equal to a plus b into pi, which is equal to b is 0, so from this we get a is equal to 0. So we get a trivial solution. Phi of x is equal to 0 has a trivial solution. Trivial solution, and this is unique. Unique solution. Unique trivial solution. So when we see the first option, a unique solution when f of lambda is equal to 0. So this is true. Infinite number of solution when f of lambda is greater than 0. Let us take f of lambda greater than 0. This is our equation. Phi double dash of x minus lambda minus 1 into phi of x is equal to 0. Phi double dash of x minus lambda minus 1 into phi of x is equal to 0. So from option B, f of lambda is greater than 0. If f of lambda is greater than 0, then this part would be m squared minus, let us take f of lambda is greater than 0 means let us take it as k squared. So we get minus k squared into phi of x is equal to 0. So we get phi double dash of x minus k squared into phi of x is equal to 0. So we get m squared minus k squared is equal to 0. M squared is equal to k squared. M is equal to plus or minus k. Hence we get the solution phi of x is equal to a e to the power kx plus b e to the power minus kx. So this will be applying the boundary conditions. Phi of phi is equal to 0, phi dash of 0 is equal to 0. Take the differentiation, phi dash of x is equal to a k e to the power kx minus b k e to the power minus kx. So phi of phi is equal to, when you apply, it is a e to the power pi x plus b e to the power minus pi x is equal to 0. And then phi dash of 0 will be equal to a k e to the power 0x plus b k minus b k e to the power 0x is equal to 0. So from first equation, we get a e to the power pi x plus b e to the power minus pi x is equal to 0. From the second equation, we get a k minus b k is equal to 0. So a k is equal to b k cancels each other. We get a is equal to b. When you apply a is equal to b in this equation, we get a e to the power pi x plus a e to the power minus pi x is equal to 0. So you can take out a e to the power pi x plus e to the power minus pi x is equal to 0. And since this part is not equal to 0, we should have a is equal to 0. That implies b is also equal to 0 since a is equal to b. Here also we get trivial solution and unique solution. Trivial solution and that is unique solution. We will see the option here. In the option, it is given an infinite number of solution when f of lambda is greater than 0. So this must be a false. So this is not true. No solution when f of lambda is less than 0. When f of lambda is less than 0, in this question, phi double dash of x minus lambda minus 1 into phi of x is equal to 0. Option C, f of lambda is less than 0. So let us take it as k squared. So we get minus k squared, already a negative. So here we have plus k squared into phi of x is equal to 0. So we get m squared plus k squared is equal to 0. That implies m squared is equal to minus k squared. That implies m is equal to plus or minus ik. So we get phi of x is equal to a cos kx plus b sin kx. Applying the boundary conditions, phi of pi is equal to 0, phi dash of 0 is equal to 0. We will find phi dash of x first, which is equal to minus ak sin kx and then plus bk cos kx. Phi of pi is equal to 0. Phi of pi is equal to a cos k pi plus b sin k pi is equal to 0. And phi dash of 0 is equal to 0. That implies phi dash of 0 is equal to minus ak sin 0 plus bk cos 0 is equal to 0. This part would be 0 since sin 0 is 0. And from this one, bk cos 0 is 1. So this is equal to 0. K is a number which is a negative number, right? We get b to be 0. So from this, apply b is equal to 0. We get a cos k pi is equal to 0. So here cos k pi is equal to 0. When is cos k pi 0? Cos k pi's are 0 for odd multiples of pi by 2. for the multiples of pi by 2. So we have k pi is equal to 2n plus 1 into pi by 2. For the odd multiples of pi by 2, we get 0. Cos 90, cos 270 and all, it is 0. So pi cancels each other. We get k is equal to 2n plus 1 by 2. This would be the eigenvalue and the corresponding eigenfunction will be equal to, as b is equal to 0, here we will have a cos kx, k is equal to 2n plus 1 by 2. So we get a cos 2n plus 1 by 2 into x. This will be the corresponding eigenfunction and this will be the eigenvalues. So we get infinitely many solutions. There exist infinitely many solutions when lambda, f of lambda is less than 0. What is given in the option? No solution for f of lambda less than 0, so it is wrong. A unique solution when lambda is greater than 1. When lambda is greater than 1, it'll have a unique solution or not. When lambda is greater than 1, what happens to the equation? When lambda is greater than 1, we get phi dash of x. Let us take lambda is equal to 2. Lambda is greater than 1 means, let us take it as 2. So we get phi double dash of x minus 2 minus 1 into phi of x is equal to 0. We get phi double dash of x minus phi of x is equal to 0. Whatever be the lambda here, whatever be the lambda which is greater than 1 will be a positive number here. Lambda minus 1 will be a positive number for lambda greater than 1. So this negative persists as it is. So we will find an equation of this type. Here it may have any constant 1, 2, 3, 4 or any constant which is a number greater than 0. Any number which is greater than 0, any positive number here. It may have any k which is positive. So this type is of this case, option B case. This case. It would be of this case. In this case, when you see here the same equation, when you see here, you find a trivial solution which is a unique solution. So option 4, we have unique solution. Yes, it is.